Hi, my name's Scott Chumbley. I'm a professor in the Material Science and Engineering Department, and I want to take a few minutes today to tell you a little bit about material science and engineering. Material science and engineering, it's a little bit different than the other basic engineering programs because, as the name kind of implies, we're kind of in between science and in between engineering. In science, you have the basic sciences of chemistry and physics, where you look at atoms and you see how things bond. And then in engineering, you take and you build things. Maybe you build an airplane, you build a car, you make some device. Well, what a material scientist does is we look at the basic building blocks of things. And so we kind of stand right in the middle. We know a little bit about chemistry and physics. We know how to put those atoms together and arrange them. And we use that to make materials that then other engineers can make stuff out of, things out of. We generally talk about three different broad categories of materials. You have metals, you have ceramics, and then you will have polymers, and then you can mix those together and make composites. Now, everything is made out of those things. As you're viewing this video, you may be sitting in a chair which has some metal parts, it has some plastic parts, and maybe it's on a concrete floor. That's the three broad classes. And I'm going to try to show you a few properties now related to material science. The first one I want to show you is just a rock. Okay, this is a rock. It's you can find it in rock shops. It's called calcite. If you look closely, you can see it's actually transparent. And what I have here on the overhead, I've just taken a piece of plastic and I put an E on there to have something to see. And now I'm going to put that piece of calcite over the top. And as you can see, now we have two E's showing up. This rock has taken the light coming from the projector and split it in such a way that I now have two images. And what's interesting, if I turn this piece of calcite around, you can see how one of those images kind of stays there and the other one moves around it, right? And that's because what this calcite is doing, it's actually polarizing the light. I have some polarized sheets here. If I take this sheet and put it in front of the overhead, you see one E, there's the other one, right? As I change the direction of the polars, I can see the two E's. And that's just a rock, right? That's why I want you to see everything has properties that we can take advantage of to make different things out of. And we do that all the time. Let me show you another one here. That's kind of an optical property. We also use optical properties a lot in communications. Maybe you've heard of fiber optics. What I have here, I'm going to make essentially what is a fiber optic cable here. Right? So I have some pieces of glass here. I'm going to put them in this flame, and I'm just going to heat it up. And of course, as I heat it up, I start to boil atoms off of these pieces of glass. That's why it turns yellow. It gets soft. And then if I pull it just right, I can make a fiber out of that glass. And you saw how easy that was. And now this is glass, remember? We think about glass being very brittle. But notice when I've made a fiber out of it, a brand new fiber, what I can do is I can take that fiber and I can bend it around. I can almost bend it back around on itself. Glass becomes brittle when it starts to be corroded by the atmosphere. And so if I took this fiber and if I coated it with a plastic coating to keep the atmosphere from getting to it, I could keep it fairly elastic like that for quite some time, and that's what we do for fiber optic cables. When we want to make a transmission line, pull the fiber, coat it quickly, and then we can pass light through that fiber and we can put different signals on each color of the light. Let me show you another little demonstration where we're going to use temperature to change properties of materials. So I'm going to start this again, this torch. And what I have here, I have a piece of steel. This is just the same material that would be in a bicycle spoke in your bicycles. It's just a medium carbon steel, and I'm going to take this one piece. I'm going to cut it in half. So I got some pliers here. So now I've got two pieces of steel, right? Came from the same piece. I'm going to take one and I'm just going to bend it and make a V. I'll put it there. And then I'll take this one and I'm going to bend it and make a V. So now I have two pieces which are pretty much identical, right? Now I'm going to use temperature to change the structure of the atoms in this piece of steel. At room temperature, the atoms in this steel, they're kind of like, you can think of having a box with an atom in the middle. I've got atoms on all the corners of the box, and then I've got one atom in the middle of the box. So we call that a body-centered cubic structure. It's just a nice cube, atom in the middle, right? And so what I'm doing now, as it becomes orange, the atoms are actually moving around. And they're moving around in that box, so instead of having one atom in the middle, I now have one atom on each of the faces of the box. We call that a face-centered cubic structure. So I'm getting it nice and hot, and then I've just got some water here. I just stuck it into the water to cool it down quickly. So there's one. All right, I really haven't changed it in anything. I'm going to take the second one, I'm going to do the exact same thing. I'm going to stick it in. Heat the material up. Those atoms are going to start moving. We call that diffusion when they start to move and jump from one space to the next. And I get it nice and hot, nice and orange, like I did for the other one. And once I have it nice and glowing orange, I stick it in the water again. Right? So right now, these two pieces are exactly the same. But I'm going to take this one. I'm just going to heat it up just a little bit, right? I keep it moving so it doesn't get too hot in any one place. It never starts glowing orange. So I'm really not changing the molecular structure of those atoms. But I am giving them a little bit of energy so that they can shuffle around and move around just a little bit, right? So here are my two pieces of steel that I had. The top one there is the one that I just heated and put in the water. The second one I heated, put in the water, and then heated it up just a little bit again. So now let's see what has happened by using temperature to move those atoms around. I'm going to take this top one here, and I'm just going to try to stretch it out and straighten it back out. Well, oh, look, it just broke. Very easily. You know, I could break it with 2 fingers. Let's do the same thing to the bottom one. I'm going to take it and I'm going to stretch it out, and I'm stretching it and I'm stretching it, and it's moving, and I'm not having any luck in getting that second one to break, right? Well, what have I done? Well, the first one broke easily, the second one didn't break at all. What I've done is a process called tempering. You've probably heard of that for your tools. All tools are said to be tempered. Tempered steel is what you have for your tools. Tempering simply means I've taken the steel, heated it up to a high temperature, cooled it quickly, and when I cool it quickly, that structure that existed at high temperature, where I have this cube with an atom on the face, that would like to get back to being a cube with an atom in the middle, but it just doesn't have time for the atoms to move around. So when I cool it rapidly, they just kind of jam themselves in however they can fit. It's a very complicated structure, and that puts a lot of strain in the material, and it makes the material brittle. But if I take that material and I heat it back up a little bit, I let those atoms move around just a little bit. Let them find a place where they can fit just a little bit more easily. And when they do that, I get back the toughness that's present in the steel. And if you look at this, you can see where it had been bent before, that hasn't moved at all, right? It's still in that exact same bend that it was. Steel becomes extremely tough when you do this tempering process, and that's why you make tools out of it. So here's a material. If you look at this, it kind of looks like a little flat pancake or brick. If you were to hold it, you would notice that it's very light. It feels like styrofoam. Well, this is actually a space shuttle tile. But notice now, because I know how to manipulate the atoms, I can produce different properties for this one. For the glass, it got hot, became very fluid in the flame. Well, notice what happens here. I'm going to take a penny. I'm going to put the penny in the space shuttle tile. I'm going to start this again. And what I'm going to do is I'm going to hold this shuttle, and normally now I would be wearing safety gloves, but I want to show the principle of this tile, which is that it's very insulating. So if I take the torch, hold this tile with my hand, apply the torch to that penny. Now the penny has a copper coating. It's actually made out of zinc on the inside, which melts much lower than the copper. I can actually melt that penny, and I'm holding the tile in my hand. It's not even hot at the back, but right in the front, right around that penny, it's hot enough. It's probably hundreds of degrees centigrade, maybe 1,000 degrees centigrade. And I can melt that penny. And yet, because of the way I put the atoms together, I'm holding it. It's not hot at all back here. Now, we've been talking about mechanical properties. I'll show you one more property here that we have. We've used heat a lot, but also, you probably know that when things get cold, that changes the properties also. I showed you the space shuttle tile. Well, when I was in graduate school, we had the Challenger explosion. Maybe you've heard of that in history. And what happened there is some of the polymer O-rings that were used in the engine apparently cracked. It was very cold the night before, and that is what happens a lot of times with polymers. As the temperature goes down, they start to get brittle because those nice elastic chains, which make things so that they can stretch, well, those chains, as they get cold, won't stretch anymore. The material can't respond the way that it used to, and so what you wind up with, instead of having something which was very elastic, you wind up with something brittle. And so what I have here is a racquetball. I put it in some liquid nitrogen so I could cool it down very quickly. I'm getting it nice and cold here. And what I'm going to do is take it out, and we'll just try kind of drop it on the floor here, and we'll see what happens. All right. So here we go. I'm going to lean over here, and it just snaps, right? And you could hear the pop because it's brittle. If you look at the pieces, these pieces are very sharp. They're cold. They're like pieces of glass right now. You have to be careful. But that certainly doesn't have the same properties it had when we were at room temperature. Now, to show you kind of some magnetic properties, what I have here, I have a piece of steel, and this is, if I can get it apart here, this is the same type of magnet that you have in all your little speakers. Now, this is a very strong magnet, right? I'm going to let it click on there, and if I tried to pull that off, I cannot pull that off. It takes about 600 pounds per square inch of force to pull that off. You can't pull it off. All you can do is kind of slide it off, right? If you slide it off, then you can get it off. These magnets are incredibly strong, and that's why they work so well for little motors. I don't need a big magnet anymore. I can use just a very tiny magnet. And of course, if I have a magnetic property, that also produces an electric property, right? The best way to illustrate that is I have a magnet here, and I have a copper tube, and I have a plastic tube, right? Now, neither one of these is magnetic. Plastic's not magnetic, copper's not magnetic, right? Neither one. Magnet's not going to stick to either one. It'll stick to steel, but it doesn't stick to copper. It doesn't stick to, a PVC pipe. But that doesn't mean that the magnet isn't having an influence on the atoms in the material, right? But it depends whether I have a polymer and the way the atoms are joined together there is different than the way I have copper and the way the atoms are joined together there, right? Here I have metallic bonding, here I can have a covalent bonding, or maybe an ionic bonding. Mostly it's covalent. But to illustrate that, what I'm going to do, I'm going to take this magnet, and before I do that, just to show you how strong these magnets are, let me show you here. I'm going to take this big magnet, and I'm going to put it on top of my hand there, and I'm going to put the smaller one below it. And I'm just going to show you that these magnets are so strong that I can attract the second magnet through about 3 or 4 inches of flesh here as it moves up my forearm. You see that? Right. That's how strong these things are. It got about right in there. Well, here's another way to show you the strength. I'm going to drop this magnet through this plastic tube here. And it's just going to fall down to the table. Just watch it. You see how long it takes. Okay, it just falls right through, right? Right? It just falls by gravity. I can kind of catch it. Well, now watch what happens when I drop it through this copper tube, right? Again, not magnetic, should fall by gravity. So I'm going to drop it. You see how long it takes? Right? Much different. Well, why? Well, it's because the magnetic field penetrates metallic materials here, like the copper, and it produces an electrical response. I don't get that in a polymer. I only get it in metallic materials. That electrical response actually acts in a direction opposite to the magnetic field. So, and you only produce it when the magnetic field is moving. If I hold it still, no field. If I move it, then I'm actually creating an electric field inside this tube, right? So when I drop it, the magnetic field is creating an electric field which pushes against it, and that slows it down. But of course, if it slows it down too much and it stops falling, then there's no electric field, so it's going to fall again. So it reaches essentially a terminal velocity where it just kind of floats down the tube, right? And you know, in the 30 years of my career, one of the big developments that came was in the area of superconductivity. Now what I have here on the table, I have a little piece of a superconductor which actually is a ceramic. That's what made it so surprising. It's not metallic at all. It is a piece of ceramic. And you don't think of ceramics as being amenable to electricity, and yet this ceramic actually conducts electricity without any loss. So what I'm going to do here is put this little magnet on top of this superconductor, and there you can see it's floating. Why is that? Well, again, you have this kind of relationship between magnetism and electricity. If you have an electrical superconductor, it does not allow any magnetic field to penetrate it. And so the magnetic field from the magnet, since it can't penetrate into the conductor, it's just suspended above it in midair, right? So again, how do we do all this? Manipulate the atoms, understand how they go together, understand how changing the properties, changing the temperature can affect all the different properties. I have one more demonstration that I'd like to show on mechanical properties. It's kind of a mixture of mechanical properties and again thermal properties. And just as you saw how I could use temperature to take these pieces of steel and make them hard, I can do the same thing with glass. And so that's what I'm going to do now. I'm going to come around front here. I've got some little step stools here. I'm going to place them there, and I have a pane of glass. Right? This is just a pane of glass, 1/8 inch thick, right? Which I can sit on those step stools. Now, This is called tempered glass. Remember we had the tempered steel? Now I've got tempered glass. And this has been treated to be strong just like I treated the steel. And what I'm going to do is I'm going to get here and stand up on the glass, right? And we'll try to get a shot that you can see that glass is actually bending just a little bit. It's very elastic, but it's taking my weight. It should actually take about 600 pounds, right? Now, how is this possible? You don't normally think about doing things like that with a pane of glass, right? Well, what we're doing is glass, when this is made, the glass is molten just as it was when I made the fiber optic, right? And in fact, the fiber optic is, I just tried, there it is. I don't know if you can see it, but it's still holding on pretty well. You can still see the two pieces. It's still fairly strong. But when I made this, as it's starting to cool down, I pour that out on a big, basically a big pool of molten metal. And of course, it just flows out across the surface of that metal, and it's all the same thickness. That's how we get it the same thickness. Well, as it's flowing away from the furnace, it's getting cooler all the time. So what I do is, as it starts to get a little bit stiff, I put big fans on it so that I blow air on both sides of it. It gets stiff enough that I can take it off the pool of metal and put it on some rollers. It's still glowing because it's still hot, but I blow air on both sides of it. And so the outside of it then starts to contract because it's getting colder. Things generally contract when they get colder. The inside is still hot, so it doesn't contract. It just kind of gets squeezed. So initially that inside is being compressed, and the outside, as it's trying to contract, it's actually in tension when it's hot. But it keeps going down the line, and now the outside is already cool, the inside's still warm, the inside's under compression, the outside's under tension, but now the inside's going to cool down. Well, what happens? Well, it wants to contract, right? But it's got this hard shell around the outside that it's connected to, so it would like to contract, but it can't. It can't contract anymore. And so when it's cool, as it cools down, it goes from being under compression to being under tension, and the outside goes from being under tension to being under compression. And so this pane of glass, even though you can't see it, the outside is under tension, or excuse me, compression. The inside is under tension. And that's what makes it strong. Compression on the outside closes up any little cracks that will form. And as long as I can keep those cracks from forming and getting bigger, the glass is very strong. But if I have a tensile force, that acts to open up cracks. Well, that's what makes cracks break. So this is strong as long as I have that outside layer, which is nice and hard. But what happens if I break through that outside layer? Well, I'm going to set up here and I'm going to show you what happens when we break through the outside layer. Now, remember, right now I've got compression on the outside, tension on the inside. So here we go. I'm going to put pliers on it. I'm just going to squeeze and try to put a chip in it and release that tensile force. There it goes. So, how have we done that? Again, understanding the material, understanding how it responds to temperature, changing the cooling rates in various parts to produce different mechanical properties. That's kind of all the demonstrations that I have time for today. Thank you very much. Again, this is Material Science and Engineering. My name is Scott Chumbley. If you have any questions, just email me at my email address, Chumbley, C-H-U-M-B-L-E-Y, @iastate.edu. Thank you very much.